On June 7, 1978, a graduate student named Diane Hartley called her professor to ask a question about wind loads. She was working on her thesis at Princeton. The question was technical, specific, and entirely routine, the kind of questions students ask professors dozens of times a year. She wanted to know how the Citicorp Center had been designed to handle quartering winds. Winds that hit a building at 45 degrees to its face, at the corner, not straight on. Her professor was William LeMessurier. He had designed the Citicorp Center himself. He told her he would look into it and call her back. He looked into it. He did the calculations. He called her back. What he told her, the record does not show in detail. What is documented is what he did next. He put down the phone. He sat at his desk. And he began to understand that the building he had designed, at the time one of the most celebrated skyscrapers in New York City, a building that had been featured in architectural journals, a building that had won awards, a building that was already fully occupied and had been for over a year, had a structural problem. Not a minor one, not a theoretical one, a problem with a specific probability attached to it, 1 in 16. That was the chance, according to his revised calculations, that a sufficiently powerful storm would cause the Citicorp Center to collapse within any given year. New York City has, on average, 1 storm per year capable of meeting that threshold. The building contained over 40 floors of occupied office space and residential apartments. It stood at the corner of 53rd Street and Lexington Avenue, in the middle of one of the densest urban environments on Earth. The engineers who later modeled a collapse scenario estimated that the debris field would cover a 10-block radius. They estimated roughly 200,000 deaths. The building had been open for a year. 17,000 people worked in it every day. LeMessurier did not call a lawyer first. He did not call his insurance company. He did not call a PR firm. He did not begin composing statements designed to minimize his liability. He did not call a colleague and ask hypothetically whether a certain kind of wind loading scenario had ever caused a problem in practice. He called the architect of record. Then he called Citicorp's chief executive. Then he called the city's buildings department. He told all of them exactly what he had found. This is a story about a building, but it is also, quietly, a story about something much rarer than a structural flaw. It is a story about what happens when a person discovers they have made a catastrophic mistake and decides to tell the truth about it. Most of the stories in this season go the other way. The Citicorp Center stands today at the corner of 53rd and Lexington. It has been renamed. It has been repaired. Almost no one who walks past it knows any of this happened. The repairs were completed in secret, at night, while the building was occupied, over a period of several months in the fall of 1978. The story did not become public until 1995, 17 years later, when a journalist named Joe Morgenstern published an account in The New Yorker. To understand why the flaw existed, and why it was the kind of flaw that could exist undetected for over a year in one of the most scrutinized construction projects in New York City, you have to understand what the building was, how it came to be built, and who William LeMessurier was. William LeMessurier was not an obscure figure. He had been a professor at Harvard. He ran a structural engineering firm in Cambridge, Massachusetts, a firm with an excellent reputation for technically ambitious projects. He was the kind of engineer who attracted the kind of architects who wanted to do things that had not been done before. He believed, and this is documented in his own writing and in the accounts of people who worked with him, that structural engineering was not purely a technical discipline, but a building's structure could be architecture too, that the bones of a building were not something to hide inside walls, but something to reveal, to celebrate, to make visible. The Citicorp Center was the project where that philosophy found its fullest expression. The Citicorp Center was completed in 1977. At 59 stories, it was the seventh tallest building in the world at the time of its completion. It remains distinctive in the Manhattan skyline for two reasons. The first is its roof, which is angled at a 45-degree slope, a feature originally intended to house solar panels, a plan that was never implemented, but which gave the building its characteristic silhouette. You can pick it out from 10 blocks away. The second reason the building is distinctive is far more unusual. The building does not sit on the ground. The Citicorp Center stands on four massive structural columns, stilts effectively, each roughly 100 feet tall, positioned not at the corners of the building's footprint, but at the center of each of its four sides. The tower floats 9 stories above street level on 4 enormous legs. From the street, you can walk under the building. There is open space at ground level that in an ordinary skyscraper would be wall and foundation. This was not an aesthetic choice, it was a constraint. The plot of land where Citicorp wanted to build was not entirely theirs. At the corner of 53rd and Lexington, there was a church. St. Peter's Lutheran Church had occupied that corner since 1862. The congregation was small, but they had a long lease, a legal position, and absolutely no interest in being relocated to make room for a bank tower. Citicorp wanted that corner. They wanted it enough to negotiate. The agreement that emerged was unusual. The church would permit the tower to be constructed above the church's footprint on the condition that a new street, Peters, designed by Hugh Stubbins, the architect of record for the entire project, fully funded by Citicorp, be built at the base of the new tower. The new church would have its own entrance, its own identity, its own street presence. It would not be subsumed by the tower. It would sit beneath and beside it, protected by the building's stilts. There was one specific requirement that shaped the entire structural design. The northeast corner of the new church's footprint could not have a structural column on it. The congregation had negotiated for that corner to be theirs. No column. Whatever held up the tower above had to avoid that corner entirely, which meant no column at the corner of 53rd and Lexington, which meant, by extension, no columns at any of the 4 corners of the tower, because a building with 3 corner columns and 1 midpoint column is structurally incoherent. LeMessurier made the decision to move all 4 columns to the midpoints of each side, creating a symmetrical structural system that accommodated the church's requirement while maintaining the building's integrity. The new St. Peter's Church stands today at the base of 601 Lexington Avenue. It is a low, dark granite structure, intentionally modest, intentionally distinct from the glass tower above it. Inside, there is a large, abstract sculpture. The congregation still worships there. They negotiated well. That positioning, columns at the midpoints of each side, rather than at the corners, was LeMessurier's elegant solution to an unusual constraint. It worked, structurally. The building's engineers ran their calculations. The structure was approved by the city. Construction proceeded. The building received extensive press coverage. LeMessurier was cited in architectural reviews as having solved an engineering problem with particular ingenuity. The building was celebrated. There was one problem that would not become visible until 1978. To understand the problem, a brief detour into how skyscrapers handle wind. A tall building in a city is not a rigid object. It flexes. In strong winds, the upper floors of a 50-story skyscraper can sway by several feet in either direction. This is not a defect, it is intentional. A completely rigid building would concentrate stress at its connections until something broke. A building that flexes, within engineered tolerances, can absorb and distribute wind forces across its entire structure. The goal of structural engineering under wind loading is not to prevent movement, but to control it. To ensure the movement stays within bounds the building was designed to tolerate. The forces that matter most are not always the ones that seem most intuitive. The obvious concern is a wind blowing directly into one face of the building, perpendicular, straight on. In the Citicorp Center's case, a north wind hitting the south face at 90 degrees, or an east wind hitting the west face. This is what most people imagine when they think about a building being stressed by wind, and this is precisely what the original structural calculations addressed. The building was designed to handle perpendicular winds at maximum historical thresholds for that location, with the required safety factors applied. The calculations passed review. The city's engineers checked them. The building was approved. The calculations were correct for perpendicular winds. The problem was the other scenario. Quartering winds hit a building at 45 degrees, at the corner, not the face. When this happens, the force distribution through the structural frame changes in ways that are not immediately obvious. In a conventional skyscraper, with columns at the four corners, quartering winds are in some ways easier to handle than perpendicular ones. The corner columns are ideally positioned to absorb and redirect diagonal loading. The geometry works in the building's favor. In the Citicorp Center, there were no corner columns. When a quartering wind loaded the structure at the northeast corner, exactly where the church had negotiated away the column, the forces had to travel further through the frame before reaching a column. The load path was longer, more complex, and it passed through a specific set of structural connections that in a conventional building would not be carrying those forces at all. Under perpendicular winds, those connections were handling their designed loads comfortably. Under quartering winds, they were being asked to do something they had not been designed for. And this is where the second discovery enters the picture. LeMessurier's original design for the structural connections at the floor trusses, the connections between the horizontal floor support structure and the vertical columns, specified welded joints. Welding creates a continuous, monolithic connection between two steel members. It is more labor-intensive than bolting, more expensive, and under most loading conditions, stronger than an equivalent bolted connection. During construction, a change was made. The change was not unusual in itself. Construction substitutions happen constantly on large projects. Materials are swapped, details are modified. Contractors propose alternatives that meet the performance specification at lower cost, and in many cases, those alternatives are perfectly adequate. The switch from welded to bolted connections at the Citicorp Center's floor trusses was reviewed and approved during construction. The review was conducted against the perpendicular wind loading specifications. It was not conducted against the quartering wind loading scenario because no one had formally run the quartering wind scenario. It was not a required check under the building codes of the time. The codes specified certain load cases. Quartering winds were not among them. The bolted connections met the code requirements. The substitution was approved. The building was built. When LeMessurier ran the quartering wind calculations in June of 1978, using the actual bolted connection specifications rather than the welded ones in his original design, he found that under diagonal wind loading at maximum storm intensity, certain connections on certain floors would fail. He found something more specific than that. He identified the exact floors. He identified the exact connections. He calculated the sequence. If the connections at these floors failed, the loads would redistribute to adjacent connections, which were already near their limits under the quartering scenario, which would then fail in sequence, which would redistribute loads further. The term for this pattern is progressive collapse, a cascade of individual failures, each one triggering the next, proceeding faster than any intervention could stop it. The Buildings Department's independent structural consultants, when they reviewed LeMessurier's findings, confirmed the analysis within weeks. He had not made an error in his June calculation. The flaw was real. The probability figure, 1 in 16, was derived from meteorological data. The threshold storm was not a hypothetical extreme. It was a storm that, According to historical weather records for New York City, the region could expect to experience roughly once every 16 years. Not once in a century, not once in recorded history, once every 16 years. The building was a year old. It was June. Hurricane season runs from June through November. This is the moment in most stories where the calculation changes, where the person holding the information begins to weigh the cost of disclosure against the cost of remaining silent, where the lawyers get involved, where the language gets careful, where the options get discussed. What LeMessurier did in the weeks following his calculation in June 1978 is, in the context of this entire season of this channel, worth stopping to examine with some care. Here is where this story diverges from every other story in this season. LeMessurier was 61 years old in the summer of 1978. He was a celebrated structural engineer with decades of work behind him. He had been a professor at Harvard. He ran a respected firm. The Citicorp Center was the signature project of his career. His name was attached to one of the most visible buildings in the New York skyline. He was also, as of June 1978, the man who knew that building was dangerous. The incentive structure at this point was not ambiguous. The flaw had been triggered by a graduate student's question. It was not something an outside inspector had found, not something a tenant had noticed, not something the city had flagged. It was buried in wind load calculations and connection specifications that required specialized knowledge to even locate, let alone evaluate. The probability of independent discovery was not zero, but it was not high. The building had passed every official review it had ever been subjected to. No one was currently looking at it. There is also the question of legal exposure. If LeMessurier disclosed the flaw, he was handing evidence of negligence directly to Citicorp, to the city, and potentially to future litigants. The disclosure itself would constitute an admission of a problem that, without the disclosure, might never come to light. His firm carried professional liability insurance, the kind of insurance that exists precisely for this situation. But insurance does not eliminate liability. It limits certain financial consequences while leaving others in place. A finding of gross negligence in the construction of a 59-story skyscraper in Manhattan is not a routine claim. The people who write about this case in engineering ethics textbooks tend to state the decision simply. LeMessurier chose professional ethics over personal interest. That framing is accurate, but it elides something. The choice was not made in the abstract. It was made by a specific person, in a specific moment, with specific things at stake. LeMessurier later said that once he understood the scope of the problem, the question of whether to disclose it felt, and this is a paraphrase, not a quotation, not like a difficult calculation, but like a simple recognition. He had created a risk for a large number of people. He was perhaps the only person in a position to eliminate that risk quickly and completely. Those two facts, taken together, told him what to do. He retained legal counsel before making his disclosure calls. He was not naive about the process, but the calls were made. He called Hugh Stubbins, the architect of record. Stubbins' initial reaction, by the accounts of people who were present, was disbelief. Not disbelief that LeMessurier was telling the truth, but disbelief at the scale of what he was hearing. The building had won awards. It had been reviewed by multiple engineering consultants during construction. It had passed every inspection, and now the man who designed its structure was telling him that under a reasonably probable storm, it would fall down. He called Citicorp. The meetings with Citicorp's executive team and their in-house engineering consultants happened over a matter of days. LeMessurier presented his calculations. Citicorp's engineers reviewed them. The confirmation came quickly. The numbers were what LeMessurier said they were. He called the New York City Buildings Department. This call is the one that most distinguishes the Citicorp story from analogous cases. Going to the regulatory authority was not legally required at the moment LeMessurier made the call. There was no statute compelling him to notify the buildings department of a structural defect he had self-identified. The disclosure was, in the technical legal sense, voluntary. The city's response, by the accounts of everyone involved, was measured and constructive. There was no immediate public announcement. There was no press conference. The decision, made by the city, in coordination with Citicorp, with LeMessurier's apparent concurrence, was to repair the building as quickly as possible and to manage the information to prevent panic. The logic of that decision deserves its own scrutiny, which we will return to shortly. The repair plan was developed over the course of July. The scope was significant. The specific bolted connections that LeMessurier had identified as vulnerable needed to be reinforced. The method was to cut and fit steel plates, essentially external bandages for the connections, and weld them in place over the existing bolted joints. The plates would cover the critical failure points, adding weld length and steel cross-section to connections that had been adequate under the original design assumptions, but were not adequate under the quartering wind scenario. The scale of the operation. Approximately 200 individual connections needed attention. They were distributed across multiple floors of a 59-story occupied building. The work would have to be done at night. This was non-negotiable. The building operated during business hours. The welding work required temporary sectioning of floors, setting up fire protection, sealing areas, running ventilation for the welding fumes. Doing this during the day, around 17,000 working occupants, was impractical and would have been impossible to explain without triggering exactly the panic the city had decided to avoid. So the welders worked nights, every night. Beginning in August of 1978, the tenants were not told. This is the one element of the story that sits uncomfortably. The people living and working in the building were not informed that their structure had a structural failure mode with a 1 in 16 annual probability. They were not told that welders were working through the night on the connections holding their offices above street level. They were not given the option to work from other locations while the repairs were underway. They were not asked whether, on balance, they would prefer to know. The decision not to tell them was made by Citicorp and the city, with the advice of public safety officials who concluded that the risks of mass panic and uncoordinated evacuation outweighed the risks of managing the situation quietly. The argument was not without logic. An announcement that a major New York skyscraper might fall down during the next big storm would produce a response that could itself cause casualties. People rushing to evacuate, traffic gridlock, the chaos of 17,000 people trying to leave a building simultaneously with no coordinated plan. The city did have an emergency evacuation plan in place. It specified that in the event of a major storm during the repair period, a storm that met or approached the threshold LeMessurier's calculations had identified, the building would be evacuated and a perimeter established. Emergency management officials were briefed. The plan was detailed and operational. Nobody in the building knew it existed. The welders came in every night through August, September, and into October. Building maintenance staff and security personnel were told that structural upgrade work was underway, a routine description that was technically accurate and contained nothing that would prompt further questions. The night crews sealed off their working sections, brought in their equipment, fitted the steel plates, and welded. A 59-story building in Manhattan does not fall silent at night. There are always people in office buildings after hours, cleaning staff, security personnel, late working employees, people retrieving forgotten items. The night repair operation had to accommodate all of this while maintaining the fiction that nothing unusual was happening. Nobody asked the wrong questions, or if they did, they received answers that satisfied them. In late August, a tropical system developed in the Atlantic. The system strengthened as it tracked northwest. Weather services issued advisories for the northeastern coast. The system was being monitored, including, with particular attention, by the engineers and officials who knew what was at stake if it made landfall near New York with sufficient intensity. The repairs were not complete in late August. The most critical connections had been addressed first, in a prioritized sequence based on LeMessurier's failure analysis. But the full scope of the work had not yet been done. The tropical system weakened before it reached the coast. It produced rain and elevated winds in New York, enough to be noticed, not enough to approach the threshold. The city watched it for 4 days. The building stood. The welders came back the following night and continued their work. By early October of 1978, the critical connections had been reinforced. LeMessurier's engineers re-ran the calculations with the new joint specifications. The building's safety factors, which had been dangerously below the required standards under the original bolted connections in the quartering wind scenario, were now comfortably above them. The repairs were declared complete. The building had been fixed. Nobody inside had known it needed fixing. Nobody outside had known either. The total cost of the repairs, approximately $8 million, covered primarily by Citicorp and the building's insurers. LeMessurier's firm's professional liability insurance paid a portion of the claim. His firm did not close. He did not lose his engineering license. He was not prosecuted. No civil suits were brought that were not resolved by the insurance settlement. He continued practicing structural engineering until his death in 2007. The story stayed out of the press for 17 years, not because of active suppression, not because anyone was threatened or paid to stay quiet. It stayed quiet because the people who knew it had resolved it, and because there was nothing to discover. No collapsed building, no body count, no investigation, no record of catastrophe in any archive. The story existed in engineering firm files, in buildings department records, and in the memories of the people who had been in the rooms when the decisions were made. Joe Morgenstern was a journalist and architecture critic. He came to the story in the mid-90s through a source in the engineering community, someone who knew someone who had been involved. He reached out to LeMessurier directly. LeMessurier was in his late 70s by then. The legal exposure from the original event had long been resolved. He had no obvious professional reason to revisit the story. He could have declined, and the story would likely have remained a rumor in engineering circles, unverifiable without a primary source willing to confirm it. He did not decline. Morgenstern's piece ran in The New Yorker in 1995. It is the primary public record of the Citicorp Center story. It is notable, as journalism goes, for what it does not do. It does not construct LeMessurier as a villain who narrowly escaped justice. It does not present the city's decision to keep tenants uninformed as a scandal. It does not reach for an outrage frame. It presents the situation as what it was. An engineer discovered a serious flaw in his own work, told the people who needed to know, and saw the problem fixed. Morgenstern was clearly aware that this was unusual. He did not need to say so explicitly. The facts were sufficient. LeMessurier spoke to Morgenstern directly and at length. He described the moment of discovery in June of 1978. He described the calculations. He described the calls. He described what it felt like to sit across a conference table from Citicorp's executives and explain that the building they had paid several $100 million for needed emergency structural repair. He was asked in various ways why he had disclosed. His answer, as Morgenstern reported it, came down to something like this. He had made a mistake that could kill a large number of people. He was perhaps the only person who understood the full scope of that mistake. And he had a chance, not guaranteed, not certain, but a genuine chance, to prevent the harm before it happened. The question of whether to disclose was, in that framing, not a question about career risk or legal exposure. It was a question about what kind of person he intended to be in the time he had remaining to make that choice. He was 61 years old when he made it. There is a separate question embedded in the Citicorp story that tends to get less attention than LeMessurier's disclosure. The question of how the flaw got there in the first place. The building codes of the 1970s did not require quartering wind analysis for new construction. They required perpendicular wind analysis. This was a gap in the code, not a gap in LeMessurier's engineering, at least not entirely. He had designed for what the code required. So had every engineer who reviewed his work. The change from welded to bolted connections during construction had been reviewed and approved against code specifications that did not include the critical load case. The building codes for new tall construction in New York and most other major American cities were revised after the Citicorp case. Quartering wind analysis became a standard requirement. The revision was not publicized as a response to the Citicorp situation. The Citicorp situation was not public, but the people within the buildings department and the structural engineering community who knew about the case understood why the revision had been made. This is how structural engineering safety standards frequently advance. Not through published disasters, but through near misses that are resolved quietly and translated into code changes that most people will never know the origin of. The Citicorp Center repair is, in that sense, a case study in a kind of institutional learning that the disaster cases do not produce. When a bridge falls, the lesson is reactive. What failed, and how do we prevent that specific failure mode from occurring in the same way again? When a building is quietly repaired before it falls, the lesson is preventive. What gap in process allowed this flaw to exist? And how do we close that gap before the next building? Reactive lessons get public commissions and extensive documentation. Preventive lessons get code revisions that appear without explanation in the new edition of the standard. The building at 53rd and Lexington is now called 601 Lexington Avenue. The slanted roof is still there. The stilts are still there. The welded steel plates that were added in the nights of August through October 1978 are still there, bonded to the building's structural frame, doing exactly what they were designed to do. There are approximately 16,000 people working in that building on any given business day. The overwhelming majority of them have never heard this story. Most of the people covered in this season did not make the calls LeMessurier made. The inventor who knew his machine was injuring workers and kept the reports in his drawer. The city official who understood the dam's spillway was insufficient and approved the maintenance deferral anyway. The company that ran the clinical trial saw the adverse event pattern in year 2 and published the results in year 5. The pattern this season is consistent. Someone knew, someone said nothing. The thing that was going to happen happened, and then there were commissions and recommendations and reports, and then the same thing happened again somewhere else. This story has a different shape. A man found a flaw in the most important thing he had ever built. He ran the numbers. He understood what the numbers meant. He understood what they would cost him. And then he picked up the phone. In this entire season, this is the closest thing to a story that ends where it should end. The problem was identified. The people who needed to know were told. The repair was made. The building stood. Nobody died. This is the part of the story that is easy to understate. It sounds like the minimum. Of course you tell the truth. Of course you fix the problem. What else would you do? The answer, based on everything in this season, is quite a lot else. For once, someone told the truth. For once, the people who were told responded appropriately. For once, the building was fixed before the storm arrived. For once. The next video covers a man named Roger Keith Coleman. He was convicted of murder in Virginia in 1982. He maintained his innocence from the first day of his trial to the last hour before his execution in 1992. His case attracted more public attention than almost any capital case in American history. Journalists, advocates, lawyers, and members of Congress argued for years that he had been wrongly convicted. After his execution, the state of Virginia agreed to permit post-conviction DNA testing of the physical evidence. The results were not what the people who had argued loudest for his innocence expected. And what happened next is the part of that story that almost nobody who covered the original case ever went back to examine. That is next.